start to introduce how to develop flood fragilities. So I'm just like gonna give a recap on what we did last time. We had a building, and I showed you this building, and we divided this building into components. And I showed you that we have almost 100 components, and we have a minimum and maximum damaging elevation for each component. And then I showed you how we can derive a truncated normal distribution for each component based on the minimum and maximum. So we use the minimum and maximum to derive a mean and standard deviation. And we use this mean and standard deviation to develop a normal distribution. Then we went back to Matlab here, and this was the code. Basically, I read the Excel sheet that I developed for the minimum and maximum flood depths, damaging flood depths for the components. And I read the mu and the standard deviation based on the minimum and maximum. Do you guys remember? If we have a minimum and maximum of a damaging elevation, so we sum them together and divide them over 2 to get the mean. And we had the rule of thumb for the standard deviation. And same thing, we did it with the replacement cost. We said, like, if we have a TV, we know that this TV might be a $300 or a $1,000 or $2,000. So we have an upper and lower bound of the replacement cost of the components. We use them to get the mean and standard deviation. And then we use this mean and standard deviation to drive a normal distribution. So this is basically what we did last time. And then we started to identify if any component fails or not. So we had to define a flood depths on an incremented flood depths, like from 0 flood depths to up to 10 meters. And then we incremented this 10 meters to using 0.01 as a flood depth step. So basically we are going 0.1, 0.2, 1.1, 1.2 up to 10 meter flood depths. And here, if you guys remember, this piece of code was like using the mean and the standard deviation for the replacement cost of the components and for the damaging elevation of the components to drive samples. Like if you have an AC unit, so you drive samples of the elevation of the AC unit, giving the upper and lower bound where this AC unit is elevated from the ground. Then we had a piece of code that see at each flood depths if this component is going to be damaged or not. And based on this, we identify the number of fails and we get the probability of failure. And then we calculated the replacement cost of the component. And if you guys remember from last time, we had this like for one component that shows you like, for example, this is, let's say it's the AC unit. So this is the normal distribution of the elevation of the AC unit, and where's the upper bound and where's the lower bound and where's the mean. So this is how it looks like in terms of a histogram. And also, if you guys remember, we had this. Do you guys remember these fragility curves? What is that? What is these curves? Fragility curves for all the components in the building. So if we have 100 components, so we have all the 100 fragilities for each component within the building. And I showed you how to develop them last time. So we did this for the components. And you guys remember how we were able to convert this from component fragility to component loss? So basically, this fragility tells you what is the probability of failure of each component at each class. If you have the replacement cost of the component, you multiply the probability of failure by the replacement cost so that you can get another set of Did I show this last time? Or just to stop the components fragility? Component fragilities? Okay. So, all right. So basically, after you get the component fragility, which is the probability of failure of the component, like K is component, at each of flood depths J, as we mentioned last time, it's the number of fails over the total number of simulations. Like we have the flood depths and we check the number of failure of the simulations, and have, for example, 400 fails out of 1,000 simulation. So the probability of failure is 400 over 1,000, which is 0.4 or 40% failure probability. The second step is to calculate the replacement cost of the component. So basically, I multiply the probability of failure by the replacement cost of the component. Like here, this is the replacement cost vector. If you guys remember, we had an upper bound, a lower bound for the replacement cost of each component. We use them to get the mean and standard deviation, and we developed, we use the function is called norm_rand to generate 1,000 simulation of the replacement cost of each component. So what I'm doing here, I'm multiplying the probability of failure by all this vector. But this vector for each component has 1,000 simulation. So what I did, I got the mean of this 1,000 simulation, and I got the standard deviation of the 1,000 simulation, because it will give you like multiple points, 1,000 replacement costs. But what I'm interested in is the mean of all these 1,000 simulation. So, and then the second step is to plot the fragility curves, and this is what we did last time. Let's see how we, and also this is the plot of the fragility curves, and this is the plot of the loss curves. Okay, so let's see how did I plot the loss curves. Let's go to figure 3. So what I did here, every curve of these is one component. This is the losses, not the fragilities. The fragilities give you the probability of failure out of 1. But for components, it's in US dollars, because I used the replacement cost. I multiplied replacement cost like $1,000 by 0.2% failure probability. So the replacement cost of the component is $200 or whatever. There are some components that are very expensive that cost maybe 30K. It says 3 multiplied by 10 to the power 4. And there is some components that like, can you see here, like this blue component? Let's see, I'm not sure. I don't have the, like every one of these color represents something. Let's see what is the blue color. The blue color. Not sure what component, but anyway. Let's go to 3. Yeah. So the component, it's like the fragility. If you guys remember the fragility, it goes up until the probability of failure hits 100%, and it then gets straight. And some of them will start from here and then get straight. Same thing with the losses. It will go from 0 to 1 and then hit straight. And then here it goes all the way like this and then hits straight until this is the maximum loss of the component. Like it has 100 probability failure. So some of the components has the threshold, like 0.5 multiplied by 10 to the power 4 will be $5,000. But the maximum we have here, some components, the yellow one, it's like 30K. So this is the differences between the components. And I also, by the way, what is the line in the middle? This is the mean, okay? And I also plotted the standard deviation, how the standard deviation look like with the losses. Let's see how did I do that. So if I go back here, yeah, so there's a function called shaded error bar. You can use this function, given you give this function the mean and the standard deviation, and this function makes a shaded bar, and you give this bar a color like transparent, and you give whatever color that you would like, and then it will plot something like what we are seeing here. It's a 3. Yeah, it only shade the like makes this shade. It doesn't plot this line in the middle. It only make this shade. You give it the mean and you give it the standard deviation, and it makes this shade, and you give it the color of the shade. And I make it transparent, like you can see what is in the back. Then after I plotted the shade, I plotted the mean, like plot D, the depths, flood depths with the mean replacement cost of each component. And give it like this plot will be done for all the components. Like if you go here, component number 1 until the number of components, and the same loop, keep looping component by component on the same figure. Like you do it in the same figure. If you want everyone in separate figure, you will have to include I here. So like you will name this figure 3 plus I. So at each component, well, figure 3 plus I, so if it's I equal to 1, so it will be figure 4, and then figure 5, figure 6. As soon as I keep it the same numbers, so they are plotting all of these in the same figure, like what I did. Then, yeah, so I have here figure 2. Yeah, so what I did here in this one, let's go back to figure 2. Figure 2, this one has small lines. What I wanted to do, I want to emphasize 5 components. Just for example, because when I publish this in a journal paper, I can't write a 96 component with color code. So what I did, I picked 5 components. I picked the garage, the AC unit, or whatever, and then I give them a color, and I give them a thick color. Can you see this is thick? This is not thick. You will find this one, blue, green, and I have maybe one yellow here, this purple. I give them a thick color, and then I plot them. Even I did this, the reviewer also has some comments like, okay, I can't understand, there's lots of curves. How about if you faded this figure, makes all of them gray and only show me this 5 components? I can't see all these components. Like, let me show you the paper actually. Let's see. Yeah, here, I'll show you exactly how this looked like in a paper. I'm not sure if it's this paper or another one. Yeah, I believe it's down there. Yeah, can you see here? So what I did here, actually it was when we submitted the paper, it was like the one that you saw them in Matlab code, but the reviewers has comments, okay, how about you faded all the curves and only emphasize this 5? So we put this 5 in different color, just like kind of paper thing, like people don't get confused. And so here emphasize the colors of 5 components. So I picked the component number 2. So if you want to know what is component number 2, you go back to the Excel sheet and you will find that component number 2 is the garage, drywall, and insulation and painting. If you go component number 9, you go back to the sheet and see what is actually component number 9. So to make the legends, I listed the name, garage drywalls, AC unit, kitchen lower cabinets for each one of these. And I put some labels, the flood depths, the probability of failure. And I believe I had the same thing with the losses for figure 3. If you guys saw it, so you will find that some of these have a thick lines and some of them have like normal line thickness. So the yellow, the green, the cyan, the purple, so all of them has a thicker lines. So that's exactly what I was doing here. I was just like giving them different line widths and different colors to emphasize these components. All right, so till now, yeah, so here, let's see, figure 4. Yeah, here figure 4 was just checking one component. So, hi. Like figure 4, I was just checking, seeing how this component look like. This here. I mean, like just like a check. Figure 5. Yeah, so figure 5, I was showing for one components what all the values that I have. Like this is the loss curve for one component. I did 1,000 simulations for each flood loss. So all of these is 1,000 curve. Like if you take a section in all these curves, it will make a normal distribution for all these points. Like each one of these is a one loss function for each simulation. So this is 1,000 curve, and this is the mean, and this is one standard deviation. So that's what we did for each one.
So each vertical line will intersect
with all these,
points.
it will make like a normal
Yeah.
distribution.
I mean, we'll have 1,000 points each.
You'll
vertical
have
line.
1,000 points.
So the most damages at the middle, the dark.
This is because of the flood depth is getting increased. Okay, so like our component, this is maybe the cabinet. The upper cabinet is here. Since the flood depth is here, the upper cabinet didn't get damaged. But once the water depths get up there, it will start to accumulate damage until at some point it will have full damage. Okay, like for example, if my cabinet is up there and the water is like 3 meters, so it's fully damaged. So if the water is 4 meters, it will still fully damaged. If the water is 8 meters, it will still fully damaged. So I'm just like drawing one curve to see how's the other curves look like and where's this standard deviation with respect to the entire like the number of simulations. So so here what I did actually I plotted D with the replacement cost. If you guys if you guys remember for figure number 3, I plotted D with the mean replacement cost. So I was only plotted the mean, not the entire sample. But what I'm doing here, I'm plotting the mean with all. Where is it? Yeah, the D with all the replacement cost values. Like if you go here to the replacement cost, this one. Look at this function. I can't see it because it's a 3D. Look at these. This is the replacement cost of all the components. It's a 94 multiplied by 1,001 multiplied by 1,000. You guys know what are these numbers? What is 94? Number of components. What is 1,001? No, this is the not the simulations. It's the number of flood depths. The 1,000, the other 1,000 is the number of simulation. So it has the components. It has the number of flood depths. So for each component, for each flood depth, it has a 1,000 simulation. So what I did here, so that I can plot this function, it's a 3D, I can plot 3D. So what I did, if we look here, I did something is called reshape. Reshape is that I'm reshaping them by the number of components and then plot them. So I take them component by component and then plot them because it's a 3D. So I reshape based on the number of components. And then this is the end depths and this is the end simulations. And then I do the same thing. I do shaded area because if you focused on figure 5, you will find that we did, this is 6. Where's figure 5? Oh, actually, I closed figure number 5. Okay, so if I want to plot figure number 5 one more time, so let's isolate it here and rerun this part. Okay, yeah, so I did a shaded area here. Can you see the shaded area? So this is basically, I'm performing this function. I give it the mean and the standard deviation and plot it on the top of the replacement cost. So this is just a plotting, like we have a bunch of data and we want to understand what is this data. So I'm trying to do lots of plots and picking what is the best plot that can fit to publish a paper. So the second part here, so right now what we did, we calculated fragilities for components, we calculated loss for components, but we didn't calculate what is the total building loss. So we have 94 components. What I want to see one curve that shows me what is the total loss for the entire building and what is the all fragilities for the entire building. So let's see how did I do the losses. I did the losses with 3 different approaches. And let's navigate how these approaches are different. So the first approach, I take the replacement cost matrix, the 3D matrix that has the 94 components and their damage corresponding to 1,001 flood depths and 1000 simulation. Okay, flood depths is from 0 to 10 at a step 0.01. This is 1000 step or 1001 step, and we have 1000 simulation. And what I get, I take the sum. Okay, let me write this so that we can understand. The replacement cost, this is metric, the replacement cost of the components. It's a 3D matrix. Let's say this is X or number 1, and this is Y or number 2, and this is C or number 3. Number 1 has 94 components. Number 2 has 1001 flood depths, and number 3 has 1000 simulations. So this is components, and this is flood depths, and this is simulation. Okay, it has 94 components, 1001 flood depths, and 1000 simulation. Okay, so what I want to do, I want to sum all these components together at each flood depths and each flood simulation. So what I did, I take the summation of which vector in this matrix. Vector 1 or vector 2 or vector 3. I want to sum vector 1, all the components, because it's a 3D matrix. So this function basically, when I ask for the sum, this function will be confused. It will sum all the metrics in one number. If you didn't write 1, if you said the sum of this matrix, it will take the summation of all this and all this and all this and make it only one single number. But this is not what I want. What I want is, I want to take the summation of all the components at each flood depths at each simulation. So basically, I want to have the flood depths and the loss for all the components. So I sum the 94 components. It will give only at flood depths, let's say it's 1 meter. It will give me 1 point. Okay. For this flood depths, I will get a flood point, but actually have a 1000 simulation. So you will end up with having 1000 point at the same flood depths. And you will do it for the next flood depths. You will end up with having 1000 point, 1000 point, 1000 point. Then you can get their mean, and then you can get your standard deviation and so on. Like what I did here. So basically, I get the summation of vector number 1, which are all the components. So this 3D matrix will be transformed into 2D matrix. Okay, like you are compressing this matrix like this to be a 2D by summing one side. The second thing, what I did here, I reshaped the matrix because it's still 3D. So I reshaped this matrix to be as a function of flood depths and the number of simulation. Because the reshaping, it will make it still 3D, but the 3D will be, rather than this one will be 94, 1001, and 1000. Okay? And well, after I do the summation, it will be 1, 1001, and 1000. It's still 3D, but the one is, this one is 1. So what I did, I reshaped to make this 1001 and 1000. So I convert it to 2D. So the 1001 is the number of depths, and the 1000 is the number of simulation. Right now, I can take the mean. So I can take the mean of this 2D matrix. But the mean is, right now I have 1000 simulations. So this matrix, I'm taking the mean of the total building loss, which is the new matrix. Let's call this total building loss. Total building loss matrix. So when I take the mean, I want to know what is the mean flood loss and even flood depths. I take the mean of which? Of the 1001 or the 1000? Which one? I'm taking the mean at each flood depth. So I take the mean of all the 1000 simulation. So it's which vector? Vector number 1 or vector number 2? It should be vector number 2. So this is the one that I want to take the mean. So I want the mean of the total building loss for vector number 2 Same thing with the standard deviation. I want the mean to the vector number, the standard deviation of the vector number 2. Right now, I have the mean total building loss and a standard deviation, and I can plot them and do the same thing, shaded area. So let's see how this figure look like, figure number 6. Okay, so this is figure number 6. So basically, each one, actually I have 1,000 curve, okay? So I end up with, this is all a 1,000 curve, and the black one is the mean. So if you take a section, you will end up having 1,000 points, and the mean is the black line, and the red line is plus and minus 1 standard deviation. Okay, does anyone have any question? It's kind of plotting, like how we can plot these things. Okay, so right now I plotted depths, flood depths with the total building loss, and this is method we didn't we didn't touch base on method 2 yet. And right now I'm done with getting the total loss function for the entire building. And that's actually, it's very easy. Just like you go read the code, it will find it very easy. You have a bunch of components got damaged, 94 components at 1,000 flood depths and 1,000 simulation. So to get the total building loss, you need to sum all the 94 components at each simulation and each flood depth, and then you plot them. You will end up with having the plot that I had a few seconds ago. That's it. Not that big deal. Just like it's all a coding matter. The second step.
For each component, the 1,000 simulation for 1,000 flood depths. This is the data we use to generate the fragility for each component, right?
Can you read that again?
Yeah, 1,000 flood depths and the 1,000 simulation.
Yeah.
These are the data we use to generate the fragility, right?
This is the data that we used to generate the fragility, but we converted them to losses by multiplying by the replacement cost of each component. So it's the same thing. So the other one was fragilities, and it's like normalized, but we take them and multiply them with the replacement cost of the component, so we converted them to dollars. Like the curve that I showed to you here, this one is dollars. Like the value here is dollars, like 1 multiplied by 10 to the power 5, $100K, and the flood depth is like 1.5 meter. If you have flood depths of 3 meters, so you will be here, you will be here, so the losses will be $200,000. So this is how we convert them from damage. This is the definition. Like some people confuse and they say damage and losses are the same thing. Damage has a definition. Like everyone has different definition of damage. Like if the door maybe has a crack, some people, okay, that's not damage. I can have the door like this. But other people, no, it's damage. I need to replace the door. So everyone has different definition of damage. But losses has a value. Like I have 100K losses or 200K losses. So this one gives us a value.
And the values of the flood depth are also lim the flood depths or
Or what?
lim?
Lim?
The log normal?
No, we used normal distributions here. If you remember, we did absolute normal. Like we have a normal distribution, gives us negative values, and we take the absolute and convert the negative values to positive values here. It's up there when we did this. If you guys, we did norm rand, and we take the absolute to convert them. If we have any negative values, so the absolute will convert them to positive value.
So even in fragility with on the x-axis, we don't have lim.
No, we don't have any line values. We don't have any log normal here. Yeah, so let's shift to the second thing, how we can convert from components fragility to buildings fragility. We have the fragility that tells us if this component fails or not, but we need to develop, this is what I was talking about, a set of damage state that describe the damage for the building. When we say that this building has a slight damage, and that's what I was telling you, everyone has different definition of slight damage. And these definitions different for earthquake, for tsunami, for flooding, each has different definition. So as you guys remember, we had an Excel sheet and we grouped the components based on the damage state. Do you guys remember? We have this one, the light gray. All these components are damage state 0. If they are damaged, we consider that the building has insignificant damage because it's still below the ground, the vertical floor elevation. like crawl space, garage. And when we're talking about the garage, like most of the homes are like at this elevation, but the garage at this elevation. So we are talking about garage damage below the first floor elevation. So it's a still insignificant damage. However, some people, okay, my garage is very important. I will not consider it insignificant damage. I will consider it slight damage. Some people can do that. So everyone has, and to be honest, when we developed these fragilities, we did 5 damage states. We did no damage, actually it's a 6, no damage, insignificant damage, slight, moderate, extensive, and complete. 6 damage states. But at some point they said we need to reduce the fragilities to only have 4 damage states. So I redo all the fragilities for all the buildings using other 4 damage states. We have, as far as I remember, no damage, moderate, extensive, complete. So what I did exactly, I grouped like these components represent insignificant. This component represents slight. This component, insignificant, slight, and moderate. I combined all these in one group. Like all these components, like from 1 up to 39 or something. And I called if any of these components are damaged, so they contribute to a moderate damage state. So this is how we define damage. So that's what I was telling you about. The definition of the damage is different from, it depends on the research. Okay, so I have these groups. So like from 1 to 6 is damage state 0, from 7 to 13 is damage state 1, 14 to 41 is damage state 2, and then we have 3, and then the final from 8 to 95 is damage state 4. So what I did here, if you guys, let's go back to the publication. I believe I explained this maybe in the introduction lecture, but let's touch base again. Yeah, here. Okay, so what I did, like we have a group of components, like let's say that we have a group of components that represent damage state 1, and they are 10 components. So how we can convert these 10 components to only one curve that tells us what is the probability of exceeding damage state 1, because these 10 represent damage state 1. So we need to do like something that's called weighted average. We need to average these components and make them only one curve that tells us what is the total probability of or the exceedance probability of damage state 1. So but how can we average them? What do you think? How can we average the component? Like if we have, for example, damage state 2 has fridge, appliances like washer, dryer, has drywalls, has lots of components. So how we can like weight average them? So the only thing that we know is their value. Some are very expensive, some of them are less expensive. Like let's take this for example. In damage state 2, we have a fridge that costs around $1,000 or $1,500, and we also have a mixer that costs maybe $15, and have lots of small components that cost $10, like $100, $150. So all of them are the same. All of them like will control the damage state the same. No, there's some of them are very expensive that the household cannot afford to replace them. So it contributes more to this damage state. So what we did is we weighted them based on the replacement cost. So what we did, we take the probability of failure. Let's show it on a curve. Yeah, here for example, these 5 curves, we need to weight them to give us only one curve. So every one of these have a different replacement cost. So we need to know what is the probability of failure at 3 meters. What is the exceedance probability at 3 meters? So to do this, I take the probability of failure of this component and the probability of failure of this component and this component and these 2 components and multiply them by their contribution to the replacement cost of the entire damage state and get only one number. So some of them are very high, some of them are very low. It gives something here in the middle based on their replacement cost. Okay, is it the replacement cost with respect to the entire building or their replacement cost with respect to the total value of the damage estate itself. It's the damage estate itself, not the entire building. So if we have 10 components and the total value of these 10 components, like for example, are 20K, and one of them is like 5K. So we divide 5K over 20K and multiply by the probability of failure of component 1. Then component 2, the value of component 2 over the 20K multiplied by the probability of failure of component 2. Here, same thing, the value of component 3 over 20K multiplied by the probability of failure. And this is what this function is doing. So it takes the replacement cost of the component and divided over the total replacement cost of the entire damage state and multiply by the probability of failure of the components. And we sum this for all the components within the damage state. And this is the Matlab code that do this procedure. So
in this equation, we have ln x, right? Fitting the fragility
Ln?
with the ln.
what is
The
like?
lognormal, right?
This is the next step. Let's wait a moment. This is the second step. Let's focus on what I said, okay? And I'm going to the log normal once we get there. Okay, so here is the mean, like I'm trying to calculate the exceedance probability of each damage state. So what I did, I started with 0 exceedance probability for each damage state, like 0 for damage state 0, 1, 2, 3, 4, up to 4, the last damage state. And then this loop made the summation, because here I'm doing this analysis, I'm calculating the contribution of component 1. So 1, and I go calculate damage state 0, and I multiply the probability of failure of component 1 at flood depths J, and I multiply by the weight, the AK20 over A24. This is from the Excel sheet. Like, let me show you. This is how I calculated the losses. If you guys remember, we have in this Excel sheet the mean replacement cost of each component. Here, this one. And this is component 1, 2, 3, 4, 5, 6. This is column number 20. And here I have the mean replacement cost of the entire damage state. So what I did in the Matlab code, I divide AK20 for component 1 over AK24, the entire replacement cost of the damage state. So this is the weight, is coming from the Excel sheet. If you guys remember from last time, A is the Excel sheet itself. And if you opened A here, the data, you will find all the values that we have in the Excel sheet. You'll find it here. This is the total replacement cost, and you will find that the replacement cost of the component somewhere here. Let's get back. Okay, so right now, I calculated damage state 0, contribution coming from component 1, okay? And then I ended the loop, but there is still another 6 loops. So I go and do the same thing for component number 2, and then here, damage state 0 will start from the damage state 0 that I have from component number 1. So here I put component number 1 and do it for, like, this is the one because I started from 0. But once I'm done with the first loop, damage state 0 has a value coming from component 1. And then another loop, so I will have damage state 0 coming from component 1 and component 2. And keep looping until I finish the 6th component. So basically, this loop is doing the summation of the 6 components. And from 1 to 6 is damage state 0, from 7 to 13, damage state 1. I do the same thing for 2, 3, up to 4. Okay, so here, I'm done with the 4 damage states. I told you at first that we will calculate the total loss for the building using 3 approaches. The first one is the one that I showed you from before. This is the second one. There is a way to calculate the losses. The first one, we calculate the loss for the building from the components, right? Multiply the probability of failure of the component by the replacement cost of the component. Here, I will get it from the whole building, the fragilities from the whole building. How? I multiply the probability of being in a damaged state by the replacement cost of the entire damaged state. So this is another way to do it. It's the same thing, but we summed some components together, 10, and we found what is their probability of failure and multiply them by the replacement cost of the whole thing. So this is one thing to do it. And you'll find the equation actually here, like it's in the same paper here. If you go down there, yeah, here's the one. So basically at each flood depths, you multiply the probability of being in damaged state I minus the probability of being in damaged state I plus 1. So this is that actually means, so if this is damaged state I and this is damaged state I plus 1, if you subtract this value from this value, it gives you the probability of being in a specific damaged state. So that's what I did. Like if you want to know at flood depths 2, what is the loss? You get this probability and multiply it by the replacement cost of this damaged state. And this probability and multiply it by the replacement cost of this damaged state. And this probability and multiply it by the replacement cost of the damaged state. Okay, because you cannot take the whole exceedance probability, because the whole exceedance probability has some contribution from damage state 2 and some contribution from damage state 3. So we separate them and taking just the probability of being in damage state 2 and multiply by the replacement cost of damage state 2. Okay, so let's see how this look like. Yeah, and here I just I have damage state 1, 2, 3 up to 4 separate, so I get them together here in this matrix. And yeah, so this is your question, Omar. So this one, so when we have fragility, what we did right now, when we calculated damage state 0, 1, 2, 3, we call these raw fragilities. Fragilities like fragility non-fitting, like you cannot fit them to a function, like it has like a random curve. But when we publish this in a papers, usually fragilities need to be fitted as a log normal CDF. That's how all the fragilities in earthquakes, the tsunamis, flooding, hurricanes, wind need to be as a CDF function. Like when we use them in practice, you have lambda and you have XC, and you use this lambda and XC to drive the fragilities, as I showed you before. But which one is more accurate? The raw fragility is the more accurate, because this is exactly represents how this function look like. The log normal fragility, when you fit them to log normal function, it's not as much accurate as the raw fragility, but it's much simpler for user to use them and much simpler for developers to capitalize on this research. So rather than giving them Excel sheets with lots of numbers, you give them two numbers, lambda and XC, and then he can generate the function as we did before. So let's see how this is doing. So actually there is a function is called log normal fitting function. And I'm going to give you this function. It's called fit search. This function, basically, you give it the, let's see. Let's see the curves here. Yeah, here. Okay, so let's maximize. The dotted line is my function, the raw fragility function. Can you see how it looks like? It's something like this, and then it goes all the way up. Some of them are like smooth, like this ones, but some of them are not smooth, like this one. So the log normal fit function, basically you give it the XY values, like the flood depths and the exceedance probability for the raw one, and it gives you another set of flood depths and exceedance probability for the fit function. So basically input output. So do this fitting. And once you fit them, it tells you what is the log normal parameter, what is the lambda, and what is the XC for each one of these. So this is actually, we have 5 fragility curves, and the dotted one is the one that is raw, and the black one is the one that is log normal fitted. So basically, this is the log normal fitting. You give the depths and the damage state for each one, like for the 5 damage state, and it gives you, if you guys familiar how to develop function on Matlab, it gives you the output depths fitted and also the CDF log normal distribution. And then you can plot them here. Okay, so what I did here, I was calculating the difference, like, okay, I calculated the flood depths, if you guys remember. So go to the paper. So if I calculated the flood loss curve from the row fragility, so this black one is the row fragility, okay, the dashed one. If I calculate the flood depths based on these row fragilities, it will be different if you calculate the flood depths based on the log normal one, because basically if you take a line like this, this will be different from this. This will be much bigger. So this is the difference. So let's see how this is going to be different, how much difference that we will have. So that's what I was doing here. I was trying to recalculate the flood loss, the mean total loss of the building using approach number 2 based on the fitted fragility and see how this is going to be different. And I plotted figure number 8. Let's see figure number 8. Okay, so here it's the same plot, but it's different colors. I was just like doing different colors. And yeah, here, so I was plotting the fitted fragility and the non-fitted fragility and giving them some legends. Okay, yeah, so here figure 9, it's a different way for plotting. Like when we publish a paper, we need the figure to be like something like this. So what I did, I want like damage state 1 has a light gray, and as the damage state is getting increased, I make it darker gray, like we have more damage. So this is basically what this piece of code is doing. This part. From here, figure number 9. So I'm making a shaded area, light gray 0, 1, 2, 3, 5, and I give them color numbers. And then I made it shaded areas for each part of these. You can maybe search this function or use them as it is, but this is how you shade with different colors. For it's a long code, like you will have to write like maybe 20 lines or 30 lines, but it gives you a better curve when we like try to publish some papers. You will get some curves like this. Okay, so with this, let's move to approach number 3 for calculating losses. So if you guys remember what we did to calculate component loss at Verist, we calculate fragilities for components by getting the probability of failure of the component and multiply this probability of failure by the replacement cost of the component. Here, we don't go through this step. We calculate the component loss directly. So for, I created component loss, like I'm starting with 0. I want to calculate the loss at each simulation for each component. So I have that simulation component. I made a 3 for loops. For loop number 1, at each depth, for each simulation, for each component, it checks if the component is damaged or not. Okay, so we basically like escaping the fragility bound. If you guys remember, this is the part that we use to get the fragility. Like we use the damage. If it's damaged, it fails, and we account the number of fails. Here, if the component is damaged, so you completely lost the component. Okay, so if the damage is more than 0, so the component loss will be the X, and then we assign a random loss value. So like we don't have an exactly loss value. We just pick a random loss value based on the distribution of the component. We have a mean and a standard deviation. So what I do here, if the component is damaged, assign a random loss for this specific component, and this is flood depth for this simulation. Take a random random component loss value. Okay. Does anybody, you guys understand this? So basically, rather than generating random samples for the replacement cost, that's what I did first, using the mean and standard deviation. So what I did here, at each flood depth, at each simulation, for each component, if the component is damaged, assign one random, normally distributed random value of the loss. Like if you have This is a normal distribution. So based on this normal distribution, you will pick one point randomly selected of the replacement cost of the component and put it here. And do this for all the components, for all the simulation, for all the flood depths. And you will end up having, let's see how we plotted this. Like figure 901. So that's how's the curve look like? If you guys remember, the other one was like lines, okay? This one is points because at each flood depth, if you cut here, you will find 1,000 number. If you cut here, you will have 1,000 value. So you will have random points with the replacement cost for each component, for each flood depth. This is one component. For each flood depth, we have 1,000 flood depths, and then for 1,000 simulation. And if you take one section in these, it will make one normal distribution for the component. So as you can see, so this is how the curve looks like. This approach is much more accurate than the other one because it captures the randomness in the replacement cost. So you see, like, you see all the points are sparse, and you see like the standard deviation is not the single line. It's something that keeps varying, but the differences is like not that big, but it's much better. Okay, so this is for one component. You can show it for any component. Okay, so I get the rand. This is only for the component loss. So I have it for all the components within the building. So I have a 3D matrix, and I did the same thing. I take the mean of the component loss. Let's write here. Component loss is a 3D matrix. This is vector number 1, 2, and 3. Vector number 1 is the depth. Let's double check. Yeah, component loss is the depth. So this is depth. Okay, because I have it here. Can you see? N the depth, and then N simulation is number 2, and N component is number 3. So this one is 1,001, and the number of simulation is 1,000, and the number of component is 94. If I want to check the component loss, can you see here, component loss? If you see, it will be 1,001 multiplied by 1,000 multiplied by 94. This is how the 3D matrix look like. So right now, this has the losses for all the components within the building. What if I want the loss for the entire building? So I will make a summation, right? At which vector? This one has depth, simulation, and components. So which one of these vectors that I want to take the sum to move from single components to the entire building? Which one? Which vector? The component number 3. So I want to take the sum. I want to compress this and take the sum of the 94 components. So if you look here, you will find that, okay, I got number 2, the mean component loss. Okay, so here is different. So here I'm getting not the total building loss. Okay, so what I'm getting here is the mean component loss. Let's get the mean component loss first. Mean component loss is, so right now I want to do the building right now. I want to do what is the mean component loss. So for the mean component loss, I have 1,000 simulation of the component loss, right? So I take the mean of the 1,000 simulation to get a 2D vector for each of the 94 component over the 1,001 simulation. So I'm getting the component verse. So I'm taking the average or the mean of the 1,000 simulation, and also getting the standard deviation. And then I plot this curve that I showed to you. This actually, I lost this one. Okay, let's run this section one more time. Yeah, so this is the one. Okay, so I kept it still components, like 94 components, and I take the average on the 1000 simulation to get it as a 2D function that has the 94 component and their flood, their losses with respect to the flood depth. Okay, so the next step is to get the total building loss, M3. So this is when you talk about total building loss, this is when you will have to sum all the component, vector number 3, this one. So I sum all the losses, the random losses from the 94 components, and I end up with having 1000 simulation for the total building loss for each flood depth, okay? So when we plot this curve, let's go to curve number 10, you'll have something like this. Okay, so this curve has each one of these points is one random loss for the entire thing after we sum the 94 components. So if you take one section, you'll end up having 1000 point, 1000 simulation, these for the entire building, because this 94 has been compressed to one building for each flood depths, and we do it for each flood depths, it will be something like this. And as you can see, like the samples here were dispersed by a little, and then it gets bigger, gets bigger, gets bigger until, because this is how we see the standard deviation look like at first, and then we go at the end. Okay, and then we got the mean, the black line, and one standard deviation, and then this is how it shows the loss function. Okay, so here as shows how did we plot this function. It's the same like you plot the flood depths with the total building loss, and this is actually method 3. And I use the shaded error to get the standard deviation. And yeah, figure 11, let's see what we have in figure 11. Yes, so figure 11, I tried to see how the different losses look like. Okay, so the black one is the loss using method 3. The blue one is the losses using fragilities. Can you see the difference? This is the Lognormal fitted fragility, like the blue one. The difference is like very, very small. Like if you plot the non-fitted fragility and you get the flood loss curve, it will coincide with this one. It will be on top of each other. If I plot the one that comes from the raw fragility, the non-fitted fragility, the two curves will be on top of each other. But since I fitted the fragility, so the fragilities are shifted a little bit. So here you will have a little bit of differences based on how is the fitting, how the raw fragility is not matching the fitted fragility. You see, like if there's like great mismatch, so there will be something like this. If they are matching, they will be close to each other. So this is how it looks like.
This is for all components, right?
Yeah, this is for the entire building. So this is the loss for the entire building. Each one of these simulation is based on summing the 94 random replacement cost for one simulation. And we have a 1000, which each one of these points, okay? All right, so the red one is the hazard stage damage function. It's a damage function that FEMA uses for this type of building. If you look at it, you will see, okay, actually hazards is very good with us until 1 meter, but after 3 meters, there is a little bit mismatch, but after 4 meters, they are totally different, right? Okay, so the difference is coming from that FEMA doesn't consider, this is a 2-story residential building. In our approach, we are going component by component. So if the building reaches some level, so we are assuming that all the buildings are damaged. Look at this one, the FEMA one. The FEMA doesn't assume that the building will never have 100% loss. But in our assumption, the building can have 100% loss. If it's fully submerged with water and every component is damaged, so we consider that the building is totally damaged. But for FEMA, it says like, okay, if the building is submerged with water, we can salvage the structural system. All the components are damaged, but we have the structure there, so we can salvage this structure. So this is how the differences come. But here we are assuming that if the flood depths reach the certain threshold, the structural system cannot work and you need to demolish the building and replace the whole building. And this is where this is coming from. Okay, so I want to show you how this results look like for a different building archetype and compare them with FEMA. So we applied this approach for 15 building archetypes. So this is 1-story residential building, and also another 1-story, but different archetype. And this is the one that we just show, archetype number 3. This is the one that have 94 components. And this is archetype number 4, multi-family 2-story residential building. This is something like a strip mall. And this is like also multi-business unit, like flexible use space. And this is something like Walmart. If you see, like for Walmart, actually we model every fridge and every aisle and everything is here, like actual real Walmart was everything. Same thing here, like a light industrial building. School, like we have a 1-story and 2-story school. Hospital, so we have a hospital like this. Community center like church. Office building and a warehouse. These are the 15 building archetypes that this approach applied to, and I'm gonna assign a homework for one of these archetypes. Like I'm gonna send you the Excel sheet and use the same code to develop one of these archetypes. So this is how the fragility look like. This is the components fragility for archetype 1, and this is the log normal fitted, not the row, because the row we don't publish raw fragility. We publish the log normal fitted fragility. And if you look here, you will find that this is the hazardous stage, the red one. The hazardous. You guys are familiar with hazardous? Have you heard this term before? Hazardous is the FEMA tool. Do you guys know FEMA? Yeah. FEMA is the Federal Emergency Management Administration. So basically, they manage disaster. They provide funds for people. They calculate losses. They have academics. They have emergency managers. They have lots of divisions, and they want to calculate losses. So they develop a tool. It's called HAZIS. This tool basically something has the same interface like ArcGIS. You add the hazard, but the HAZIS tool, you add the hazard, and they have damage functions. And they calculate the losses for you, like it tells you the losses. So this is the function is derived from HAZIS. If you look, you will find that the function that we developed has much more better match than the one that we developed. So, and everyone has a reason, like why? Because HAZIS doesn't have the same archetypes that we have, and they have their own assumptions, and we have our own assumptions. So definitely they will not 100% match together. Okay, and next time we're gonna see how we develop flood loss surface, but I'm gonna only show you the 2D. So this is the 2D of the loss. This is for archetype 2. How's the functions look like? And archetype 3, this is the one that we developed, and this is how it looks like, the one that we just did today. Here, archetype number 4. 5, this is how 5 look like. This is one of the business buildings. Also, this is how the losses look like method 1 and method 2. You know, actually, what is method 1 and method? So we didn't publish the 3 methods. It's only because one of them are like synced to each other, like the first one, and I believe the second one are the same like each other, but we published the one that is derived from the fragility because like when we calculate losses, this loss function doesn't fit anything. Like you will have to have an XY values, and you do fitting. Like if you have flood depths is 5 meters, you go and interpolate in this function and get losses. You'll need to have XY values, but you can do one very quick thing. If you have the fragilities, you have the lambda and XC for the fragilities, you can get the blue one very quickly by multiplying the probability of being in each damage state by the replacement post of each damage state. So you can get the blue one. So we usually use the blue one, but this is one is the more accurate. But the differences are very, very small. That's why we needed to publish the both methods. Yeah, so here, and actually I'm gonna send you this paper just to have a look on how these functions are developed. If you need to know more about the components, the archetypes, and everything, it might help you a lot. So with this, I'm done with the lecture today. I'm just like what I mentioned, I'm gonna assign homework number 5, and it will include developing a HICRAS model, hazard map, and developing a fragility model. So it will have 2 activities, right? Okay, so that's it for today.